Welcome to the place where we gain knowledge through the lens of creativity. I am Aaron Dworkin, and this is Artful Science. Thanks again for joining me here on Artful Science. Today's show is Cygnss, Navigating the Earth from Space. And my guest is Chris Ruff, who serves as the Frederick Bartman Collegiate Professor of Climate and Space Science, leads the Remote Sensing Group in the Climate and Space Sciences and Engineering Department, otherwise known as CLASP, at the College of Engineering here at the University of Michigan. Chris, welcome to the show.
Oh, thank you. Thanks for having me.
I love these long introductions. So this is just fascinating work that you do. And as I mentioned, you lead this remote sensing group at Michigan. So I think first, especially for our audience and a lot of people who are not in the sciences, let's just understand what is remote sensing actually, and how does it work?
Right. So remote sensing in general means, sensing something remotely, like not touching it when you sense it. And like in everyday life, an example of a remote sensing instrument is the thing that you kind of point towards your ear to see what your temperature is. And that it's got a little infrared sensor in it that measures infrared radiation given off by your ear. And there's very similar types of sensors on a whole bunch of satellites that look down at the Earth and measure the temperature of the Earth exactly with the exact same technology. So that's an example. There's a lot of other kinds of remote sensing, but they're a really useful way from satellites to tell what the Earth is doing.
Wow. And that's just extraordinary. And so using this type of sensing literally from space, we can gather a lot of this information, and that similar type of information, which can be detected, I assume, to very, very small or detailed specificity, even though it's such a long distance.
Right. The equipment on satellites is a little bit more sophisticated than the thermometers, but it's the same general idea. Yeah.
Right. Awesome. So as part of, this type of work, you helped to develop Cygnss, which is NASA's Cyclone Global Navigation Satellite System mission. So what is that, and what is its function? What does it do?
Right. So it's a kind of remote sensing system, and it leverages the GPS satellites that are already up there. GPS is a subset of this type of satellite called Global Navigation Satellite System. They're navigation satellites. It was the first one, and it's the biggest one, but there's now a number of others that other countries fly.
Right.
And those systems.
And sorry, just to interrupt you, and that's what we all know as, guides our phones to, our apps to figure out where we're going and all that, right? They're all using those GPS satellites.
Absolutely. It's that navigation signal that your cell phone or your car uses. So we have on our satellites, they're the Cygnss satellites, we've modified some commercial GPS receivers, kind of like the kind that are in your car. And they look down at the Earth. And when the GPS navigation signals go down from the GPS satellites, they reflect off the Earth back into space, and we measure those reflected signals. And by analyzing how the navigation information is distorted when it reflects off the Earth's surface, we can unscramble that and figure out a lot of details about the Earth's surface itself. And it's a kind of remote sensing.
Wow. So, and just so that I can kind of understand, is there kind of an example you can give of what is the type of information we can learn about the Earth by kind of getting basically those reflected signals, and by how they've changed since they came to Earth, we can learn about it? Is there an example of what we might learn?
So the original Cygnss mission, when it was launched 5 years ago, had one particular science objective, and that was to measure how strong winds are in hurricanes. So whenever one of our satellites goes over a hurricane, it looks down and sees the GPS reflected signals from the water right in the middle of the hurricane. And the stronger the wind blows, the rougher the surface gets. And the rougher the surface is, the more distorted the GPS signal gets. so we can accurately measure exactly how windy it is in the middle of a hurricane using this technique. And that was the original purpose of the mission.
Wow.
And it works. And we now take that wind information and assimilate it into forecast models, hurricane numerical forecast models, to help improve the quality of the forecasts.
Gotcha. So, and of course, right, I was thinking that we usually get all this information from those hurricane hunters, the planes we hear about that dive into a hurricane and check stuff out. But just so that I'm kind of clear on it as I try to understand the science behind it, that basically we're beaming that GPS signal down that otherwise might come to our cars, goes through, hits the surface of the water, reflected back up. And because of the level of disturbance of water, we can literally understand that to the minutest detail to literally know exactly the wind speed at that particular time. Is that basically, in a rudimentary way,
No, that's exactly what we're doing. And we've actually used those Hurricane Hunter airplane measurements as validation for our satellite measurements. I actually flew on it in Hurricane Harvey. They let me fly on it because of the Cygnss mission. And we were doing those flights to validate our measurements of the winds in Harvey. And that was an exciting day.
Wow. So, and as a complete side note, what is that like being in a Hurricane Hunter plane? I assume it's a much different experience than a regular.
A little bumpy.
Awesome. Well, this is great. And what I always kind of like to do on the show is to kind of get things to how understand the basis of the science, but then understand kind of how is that relevant to us. So in other words, approaching this from a layperson, from an artist's point of view, this knowledge about wind speed or other things we can learn from Cygnss, how does that impact us or further us, impact us as a society?
Right. Well, the hurricane component of the mission, I mean, we improve the skill of hurricane forecasts. So we improve forecasts of where they're going to go, where they're going to make landfall, how strong they're going to be, how strong the storm surge is going to be. I mean, all the sorts of things that you would like to know to prepare in advance, or whether to evacuate, what parts of the coastline to evacuate. Those sort of practical things are all, benefits of making these measurements better. So that's an immediate impact from the mission objectives. Since we've been up there, we only spend, I don't know, 1/100% or less of our time actually over hurricanes, because the orbits are just going around the world all the time. So there's a lot of data that has nothing to do with hurricanes. And since we've been up there, we've spent a lot of time looking at all that other data to see what else we can do with these satellites. And there's been a number of other applications that have kind of popped up that weren't really anticipated. And those also have a lot of societal implications. One example, when we're over land, the scattering of the GPS signals tells you a lot of information about the moisture content of the soil just below the surface. That it turns out that affects the reflections. And a nice thing about that is the GPS signals will go through trees and leaves just fine. That's why your GPS works when you're hiking in the forest. And so we're able to measure how moist the soil is below vegetation, which is something that's very difficult to do otherwise from a satellite. And we've been using that information, working with a United Nations organization in Africa that tries to track down and identify outbreaks of locusts, because they have a big locust problem there that damages their agriculture. So we've been identifying where there's moist soil under the vegetation. Other satellites measure how healthy the vegetation is. And when you have the combination of healthy vegetation and moisture under the leaves, that's the perfect combination for breeding locusts, it turns out. So when we find these two conditions together, we let the people there know, and they fly their eradication airplanes with insecticides or pesticides or something to go kill the locust larvae. So that's a totally cool application that we had no idea about before the mission started.
Wow, it's extraordinary. And seeing this kind of arc of science, how developing a method or a way to, gain data and information without even fully knowing the long-term implications. And just kind of going on that further, any additional kind of long-term implications that you see, environmental impact? I've read something about, plastics in the oceans and things like that. Are there some long-term things and implications that you see?
Right. So the ocean microplastics, that's another interesting little side, capability we weren't expecting. So there's a lot of ways to measure the wind over ocean, from numerical weather forecast models and buoys and other satellites. The thing that Cygnss did that was unusual and useful was being able to measure them in hurricanes, because that's an especially hard thing to do. But in other parts of the ocean, most of the ocean, when there's no hurricanes, you can predict what the wind is going to be many different ways. So we take that wind information and calculate how rough the surface should be and how much the GPS signals should be distorted from somebody else's wind information. And then we compare that to our measurements. And when the ocean is very clean, they agree very, very well. But it turns out that the disagreement between what we measure as the roughness and how rough the ocean actually is, or how rough it should be from the wind, they're different. And the difference is highly correlated with the concentration of ocean microplastics. So we can image the distribution of microplastics and where it is and where it isn't and how it changes over time with this technique. It's something we weren't expecting at all, that in the last year we've kind of figured out how to do it. And now we can make these time-lapse images, for example, of microplastics coming out of the river mouths of some of the big rivers in the world, the Yangtze, the Ganges, the Mississippi. We see these outflows of microplastic into the ocean, and then we can track where they go and track where they accumulate. Like the Great Pacific Garbage Patch in the North Pacific stands out in our imagery very clearly. So that's useful, I think, just as an indicator of the problem to help raise its visibility. There's also a number of organizations that have fleets of ships that go out to clean up the plastics. There's one in Seattle, there's one in the Netherlands, there's one in Finland. And we've been talking and working with them, sharing our data, and as a way to help inform them about the most efficient and effective places to deploy their ships, where there's lots of plastics. And they're also making measurements while they clean up the ocean of what plastic is there. And we use that information to help train our algorithms. So it's kind of a win-win thing.
Truly extraordinary, and obviously such, close to home impact for all of us, and especially for the long term. Unfortunately, we're just about out of time, but I always like to ask of all my guests, since we're here at the intersection of arts and sciences, do you have any arts discipline that you like to practice yourself or that you appreciate?
Yeah, actually, I guess I am, but I was more in the past a musician, and it actually kind of got me into the satellite business, actually, believe it or not. So I was a physics major as an undergrad, and I just always assumed I was going to be a physicist someday and go to grad school and get a PhD in physics. But I was also playing in blues bands, I'm a guitarist. And when I was playing in the bands and I started getting into the electronic side of it, building like sound effects and special effects boxes. And then I got more into it and built a synthesizer and a PA system and got really into the electronics, building them, and decided that was what I really loved to do. So I switched from physics to electrical engineering, went to grad school in electrical engineering, and got into the design of remote sensing instruments for satellites as a grad student. And I've been doing it ever since. So yeah, it worked out really nicely.
Wow, a true connection of the arts leading to the sciences.
Yeah.
Well, Chris Ruff, thank you for helping us gain knowledge through the lens of creativity here on Artful Science.
Yeah, I was very happy. Yeah, thanks for asking me to come.